Hi, my name is Yuhang. I'm from EPFL Multimedia Signal Processing Group. Welcome to my presentation for our paper towards visual saliency explanations of face verification. Here is the outline of my presentation. I will start with a brief introduction to the topic of explainable face verification, and then I will introduce our proposed methods as well as the evaluation methodology. The experimental results are presented afterwards and followed by a conclusion. Our work focuses on the problem of explainable face verification. Basically, it aims to interpret why a face recognition model decides to match or not match a given facial image with another. It is a very important topic because face recognition technology has become one of the most widely used computer vision applications. During real-world usage, the user should at least be able to understand why the face recognition model accepts or rejects the input face images. However, the decision-making process of the current deep face recognition model is still a black box, and the field of explainable face recognition is still underexplored. The most popular way to perform explainable face verification is to provide visual saliency maps to highlight the discriminative regions. There are typically two types of methods nowadays. The model-specific methods integrates the explainability modules into the face recognition system, while the model-agnostic methods often apply external explainability tools to face recognition model. However, the main drawback of current explainable face verification methods is that they only provide similarity maps as explanation, but we believe that the dissimilar parts are equally important, as they might dominate the decision-making process when the inputs are imposter pairs. Therefore, we give a new definition for the explanation of face verification. If the face verification system believes the input pair is matching, the saliency map should highlight the facial regions that are similar to the model. On the other hand, if the model believes the input pair is not matching, the saliency map should highlight the dissimilar regions between the input faces. We present a new model-agnostic explanation method called CorrRISE to address the new definition of explainable face verification. It provides saliency maps for both similarity and dissimilarity regions between two face images, and it consists of two steps: mask generation and saliency map calculation. In the first step, we iteratively generate masks as perturbations. For each mask, we sample multiple square patches with arbitrary values between 0 and 1 and in random locations. And during each iteration, we apply the generated mask to the facial image and calculate the similarity score. The list of masks and the similarity scores after each iteration have been collected for the next steps. In the saliency map calculation step, we perform pixel-wise Pearson correlation between the list of similarity scores and the list of values of masks at pixel ij. This step will be calculated iteratively for each pixel of the image, and the correlation coefficients at each pixel is calculated individually. The positive coefficients will represent the similar regions, while the negative values will represent the dissimilar regions. Under this explanation framework, we can obtain both similarity and dissimilarity saliency maps for each input image. Despite the development of explainable face verification, the importance of rigorous evaluation methodologies has been overlooked. In this work, we propose new deletion and insertion matrix to better fit explanation methods for face verification. As shown in the figure and the algorithm, for the deletion matrix, assuming we have saliency maps for dataset D, we first sort each saliency map according to the importance value. Then, we mask the first p% of most salient pixels of the entire dataset, and then get a D prime. And then, we perform a verification task using the new dataset D prime and report the accuracy. After iterating from 0% to 100% of deletions, we plot the curve of verification accuracy versus the percentage of masked pixels, and then report the AUC score as the final deletion matrix. For the insertion matrix, we take a complementary approach by inserting the most important pixels into a plain image. But in principle, we will perform the similar procedures as the deletion matrix. As for experimental results, We start by presenting some visual results in standard verification scenarios. As shown in the figure, for those genuine pairs, the produced saliency maps can probably highlight regions that the face recognition model believes are very similar, such as the cheeks in the first row and the nose regions in the second and fourth rows. Meanwhile, they also indicate the background and heads are dissimilar regions. On the other hand, for those imposed pairs, the saliency map clearly depicts the dissimilar regions between the two images, such as the eye regions in the fourth row. In real-world situations, face verification systems can suffer from various challenging situations, such as occlusion or pose variation, and sometimes even give wrong predictions. In the figure on the left, the face verification model managed to give correct predictions on all these occluded face pairs, and it is notable that CorrRISE can precisely identify the non-occluded parts as similar regions and occluded parts as dissimilar regions. The figure on the right shows the post-irradiation situation, and the face recognition actually fails to verify the face pairs in row 3 and row 4. And the dissimilar saliency map actually explains that the face verification model fails at row 3 because of the missing eye regions in the post-biased face. Furthermore, we make a comparison with other explanation approaches, including current state-of-the-art model-agnostic explainable face verification methods, as well as some direct adaptations of famous general explainable artificial intelligence tools. It is notable that CorrRISE consistently obtains more stable saliency maps than other approaches, and can always precisely highlight the most similar regions between any given input pairs. In addition to visual demonstration, we conduct a quantitative evaluation using our proposed deletion insertion matrix for a fair comparison. The experiments have been performed on 3 datasets, representing 3 different verification scenarios. As shown in the table, the quantitative matrix have shown that the CorrRISE is capable of providing more precise saliency maps for all 3 datasets. In conclusion, we first provide a more reasonable definition of explanation for face verification. Secondly, we propose the CorrRISE algorithm that can produce saliency maps for both similarity and dissimilarity regions between any 2 facial images. It outperforms the current state-of-the-art explainable face verification methods both visually and quantitatively. Last but not least, we conceive a new quantitative evaluation methodology for general explainable face verification methods. In the future, we plan to further improve the evaluation methodology to measure the accuracy of similarity map and dissimilarity map separately. We also would like to investigate, by subjective experiments, whether the explanations can help humans better understand the decision of the deep face recognition models. Thank you for your attention. For any questions, please contact the author through the following email address.